our focus today is going to be how do we move from a secant line, which passes through the curve at 2 points, to a tangent line, which passes through the curve, well, touches the curve at exactly 1 point. The tangent line is going to lead us into the very important concept in calculus called the derivative. The derivative can be thought of as the slope of a function at a specific point. So the slope of f of x at x equals a. This also could be then the slope of the tangent line to f of x at x equals a. This could be equal to the instantaneous rate of change. Rate of change is another way of saying slope, right? The instantaneous rate of change of f at a. So instantaneous rate of change, the slope of the curve, the slope of the tangent line, all of these things are going to be kind of used interchangeably when we start talking about the derivative. But all of them mean find the same thing. And the way we find the derivative is going to be using a limit, which we'll get here in just a second. So again, slope is rate of change. You've studied slope in a lot of your math classes and science classes too. So slope is often used with the letter m. And we're used to finding slopes of lines, where the slope is constant, right? You have a slope of 3, you have a slope of 5, you have a slope of 7, whatever it might be. And to find that slope, you find the rise over the run. That's how we first learn it, which then really means that you're going to take y2 minus y1 over x2 minus x1. You'll find the rate of change between those 2 points. That creates your slope. In science class, you might see it as the change in y over the change in x, delta y over delta x. The idea, though, is that a slope of a line is constant. Well, we want to talk then about how do we find the slope of a curve. The slopes over here are negative. The slopes here, right there, is 0. Then the slopes change and turn positive. So the slope is changing depending on what part of the curve you're located at. So let's say I wanted to find the slope of the curve at this moment, at A. Well, that's the point A, comma, f of A. What I can do is I can use another point kind of nearby, we'll call it B, comma, f of B, and I could find the slope of that red line. And the slope of the red line would be an okay estimate of the slope of that blue line. Wow, that blue line's not drawn very well. Let me do that again. That blue line has a little bit of a positive slope. So the red line's like an okay estimation, but I can find it. The change in y, the output at B, minus the output at A, over B minus A, and that would give me the slope of the secant line, which is nearby the blue dot that I'm curious, the blue line that I want, right? This is where I actually want the slope. The slope of the secant is an okay approximation. Okay, so in goes B, out comes f of B, in goes A, out comes f of A. A was really the point where I wanted that slope. So slope is a rate of change, but how do we move from the slope of the secant line to instead be that perfect blue tangent line slope? Well, we're going to look at that by letting our A be equal to x and B be equal to x plus h. So let's go ahead and set up our picture. And I had that purple curve. I wanted to know the slope at this moment, A, but it says that we're going to let A be equal to x. So I'll put x there. And then B is supposed to be equal to x plus h. So I'm going to label my point that had an input of B, but instead I'll call that x plus h. This then was my red secant line. My red secant line would have had an input of x plus h and an output of f of x plus h, minus, minus. The input of A, which in this case was x, the output, that was f of A, or f of x. Okay, so this is still my slope of my red line, and you're probably like, that's what we just did on the previous one. Now you've just made it more complicated with x's and h's. Yes and no. Let's think about then what would make this red line turn perfectly into the tangent line, that when we zoom in, we're locally linear with the purple. The blue and the purple are the same. Everything's good. Well, hopefully you're saying I'd like for this green dot to move closer and closer and closer and closer to the blue dot, right? Make a really, 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 really specific secant line where the distance between your 2 points, we'll call it h, where the distance between those 2 points approaches 0. So you're closing in from x to x plus h, you're closing in h, letting it become smaller and smaller and smaller and smaller. And that is how we get our limit definition of the derivative. So the limit as h approaches 0, in the numerator, I've got f of x plus h minus f of x. In the denominator, my x's subtract, and so we see it with just h. This is what we call f prime of x. This is the derivative of f at x. So this would find us the slope anywhere. We could do this, and then if we knew our x value, we would just plug in our x value, and we would get the slope of that blue tangent line. Again, we read that f prime of x means do this. Well, f prime means find the derivative, so find the instantaneous rate of change, the slope of the tangent line, the slope at a moment, the slope at an instant. Let's see what it looks like in an example. We've moved our secant line 2 points to be infinitely close together at 1 point, thus creating the tangent line. Find the slope of the tangent line. Okay, slope of the tangent line really just means find the derivative. And finding the derivative for us right now just means find f prime of x. Knowing that our function is 3x squared plus 4, and we would like to be at the point when x is equal to 2. All right, well, there's a couple of different ways that we could do this. I'm going to use the limit formula that we just wrote down. I'm supposed to find the limit as h approaches 0 of f of x plus h minus f of x all over h. And that would give me my f prime of x. Okay, well, let's use our function then. Our function said 3x squared, limit as h goes to 0, 3x squared. So I'm going to take 3x plus h squared plus 4. Okay, so f of x plus h is 3x plus h's squared plus 4 minus my f of x in its original form, which was 3x squared plus 4 all over h. And I'm going to do this limit because that's what we've been practicing. Well, limit starts with direct substitution. If I plug in 0 for h, I end up with 0 over 0. So I'm going to keep going. If you feel like you can keep going without watching my every step, go for it. I'm going to keep going by taking, I should change colors, taking this quantity, x plus h, and actually squaring it, which will get me x squared plus 2xh plus h squared. I still have a plus 4 minus, I'm going to distribute this, so minus 3x squared minus 4, still dividing by h. Well, just like all of our limit work to this point, we want to actually do some cleanup work. So this is the limit as h approaches 0. Yes, I'm writing limit every single time because I'm so good at my limit notation. So I'm distributing that 3 in hopes that something will cancel out at some point. And we lose the 3x squareds. We lose the 4s. And then each one of these terms has an h, an h, and an h. So what I have is a brand new limit problem. The limit as h approaches 0, 6x plus 3h. Well, if I let h go to 0 with direct substitution, I end up with an answer of 6x. which means that the derivative of that function at any x value is equal to 6 times x. I didn't want the derivative anywhere. I wanted to find the derivative, the slope of the tangent line, specifically at 2. So I'm going to plug in 2 to say, hey, what's going on at 2? Well, f prime of 2 then will be equal to 12. And the slope of our tangent line at the point 2, 16, the slope is 12, which in calculus we would say f prime of 2 is 12. We no longer need the letter m. I'm leaving it there for a reason. You'll see why in just a sec. So let's look from a graph point. Here's our function. Here's my point 2 comma f of 2 that I would like to find the tangent line, or the slope of the tangent line. Makes sense that this would have a slope of 12. Pretty positive slope going on. Great. I can take this a step further and say, I know how to write the equation of that tangent line. It's not asking me to, but I can, because why not? I know I'm supposed to go through the point 2, 16, and I know I'm supposed to have a slope of 12. Okay, well, the point 2, 16, x1, y1, and the slope at 2 was equal to 12. So if I put this into Desmos, which I did down here, look at this blue tangent line, right? The tangent line touches exactly at the green dot, but if I zoom in close enough, because the purple curve is smooth, locally linear, the slope of the blue line is representing the slope of the purple curve at that green point. They are one and the same because of local linearity. I found the slope of the tangent line at x equals 2 was 12, which represents the slope of the curve, the slope of the tangent line, the derivative. All right, you got a little bit more. It's the alternate form. The alternate form can be useful when finding just f prime of a, and that one, oops, that's a limit, is the limit as x approaches a of f of x minus f of a all over x minus a. And this is useful when you know that you're looking to find the slope specifically at your input of a. So you already know, hey, I want the slope at, in our last one we could have used this form, we wanted the slope just at 2, as opposed to finding f prime of x, which finds you the slope anywhere. And each one has its own purposes. So I gave you kind of a nice summary. The alternate derivative is equivalent to the limit definition or difference quotient that we've used before. It's just an alternate way to define the derivative using a limit. So most often, if you are looking to find the slope at a specific a value, you'll want to use that alternate definition. You don't have to, okay? You could use this one. This one will find you the derivative of any x value, right? And then at the end, just sub in what your a value was, and that's perfectly fine too, okay? The reason why I've even mentioned the purple one is this is super useful for piecewise functions. And we're going to see that in class over the next couple weeks. Super, super useful for piecewise because the blue one gets really complicated with those piecewise functions. And so if you know you're just curious about the slope at, let's say, 5, and you've got to do the slope from the left and the slope from the right, you might as well just use the purple alternate definition. It'll work much faster for you, okay? But technically speaking, they do the same thing. This one, you plug in a first. See all those a's going on? A's, 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 A's. Versus this one, you just find everything left in terms of x's, and at the end, you could plug in your x value. We'll talk more about the limit definition of the derivative and the, quote, alternate form over the next couple of days, but for right now, this is a good reference page for you when you're asked to find different things.